Find the area of the region bounded by the graph of the function f of x equals 3x squared plus 1, the x-axis, and the lines x equals 0 and x equals 2. All right, so let's see what we're working with here. We have the parabola 3x squared plus, or the graph of 3x squared plus 1 is the parabola. It looks something like this. It's shifted up 1. It's a little skinnier than x squared because of the 3 out front. We have the x-axis, which is here. We have the vertical lines, x equals 0 and x equals 2. So it looks like we have this area in here under the graph and between these two vertical lines. Okay, so we're looking for this area. Now, it's important to note that the area is not always equal to the definite integral, but if there's no negative y values, if the function is non-negative on your interval, in this case the interval is 0 to 2 on the x-axis, if your function is non-negative, then the area under that graph is equal to the definite integral, in this case from 0 to 2, of f of x, which is 3x squared plus 1, dx. And this problem might look familiar because I've done it already. This is the exact problem, word for word, I've already done in a previous video. And in that previous video, we solved using Riemann sums. We solved using rectangles. And we said, well, the area is equal to the limit as the number of rectangles goes to infinity of the sum of those rectangles. And another way of thinking about the n going to infinity, or the number of rectangles going to infinity, is also saying the width of the widest rectangle goes to 0. So either way, as I goes from 1 to n, so we're taking the sum of the area of all those rectangles, and the area of a rectangle is base times height. We actually write it as height times base, and it's f of mi. We used right endpoints in my previous video times the base, which is delta x. And I'm not going to go through the whole process because there's quite a bit of algebra in there, but there was a number of steps of algebra, and we ended up with the limit as n approaches infinity of 10 plus 12 over n plus 4 over n squared. Now, if you want to connect the dots here, you'd have to watch my other video where I use the limits of sums, or the Riemann sums, to solve this. And if we take the limit as n goes to infinity, this second term goes to 0, the third term goes to 0, and we got 10 square units. Okay, well, in this video, I'm going to use another method, actually a much more succinct, a much more streamlined method. I'm going to use the fundamental theorem of calculus. And the fundamental theorem of calculus says, fundamental theorem of calculus. The fundamental theorem of calculus says that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is an antiderivative of f of x. All right, so we've already talked about finding antiderivatives, or indefinite integrals. So let's use the fundamental theorem of calculus. So we're saying the area is equal to, and I'm just going to copy what's up here in blue. The area is equal to the integral from 0 to 2 of 3x squared plus 1 dx. Well, let's take an antiderivative of, well, let's go term by term. The antiderivative of 3x squared. Well, I'll show all of the work. You may not write every single step that I'm writing, but just for the sake of this video, there's a 3, and the antiderivative of x squared is x cubed over 3, plus the antiderivative of x, or the antiderivative of 1 is x. I was getting ahead of myself. And we don't need the plus c. Now, the reason we don't need the plus c with definite integrals is, well, let's think about this. If we look at the fundamental theorem of calculus, which is right here, capital F is an antiderivative of f of x. So for that capital F, you're going to have a plus c here, and you're also going to have a plus c here. And because it's subtraction, you have the c minus c, the plus c's will cancel. So you could use any value of c, so you might as well use 0, because it's, you know, that's the simplest one. So the value of c doesn't matter because of the subtraction, because you have a c on the first term, or plus c on the first term, a plus c on the second term, they cancel out. All right, so here's our antiderivative of 3x squared plus 1, and we're going to evaluate that. So this vertical bar means evaluating from x equals 0 to x equals 2. And what we're doing is we're exactly plugging in 2 into our antiderivative. So the 3's cancel. So that's just x to the third power. So that's 2 to the third power plus 2 minus 0 to the third power plus 0. All right, and this is the fundamental theorem of calculus. And we get exactly what we got before. 2 to the third power is 8, plus 2 is 10. And we're subtracting 0. 10 minus 0 is 10. So you'll see that this is a much quicker way of evaluating definite integrals. I mean, if your goal is to evaluate a definite integral quickly, then use the fundamental theorem of calculus. Using Riemann sums and limits of summations is always going to take longer than the fundamental theorem of calculus. So moving forward, this is going to be our guy. We're going to be using the fundamental theorem of calculus. Okay, so that about does it for this first introductory video into the fundamental theorem of calculus. And like I said, if you want to know the full details of this process, I mean, there's many steps. This was like 7 or 8 or 9 steps of algebra here. I have another video where I solve this exact same problem using Riemann sums. Okay, that does it for this one. I hope it was helpful.